All right, so chapter 7. Chapter 7 is real short, and it's really easy. All right? Yesterday, 8th period, we got done with it within an hour. Okay? So chapter 7 is on ionic and metallic bonding. So kind of as a review, what are ions?
It's an atom with like one more electron or one less electron than it should.
Okay, so one way that we can kind of say that what ions are, atoms with a charge. Okay, now how do we get this charge on the atom? We have an offset of protons and electrons. And with this, we're going to be looking at a particular type of electron. We're going to be looking at valence electrons. Does anybody remember what valence electrons are?
They're the electrons in like the outermost shell.
Yes. Electrons in the outermost, or in some books they might say highest energy level. Okay, any questions there? Kind of a quick review from last semester, just a little bit. Now, there's a couple different ways that we can actually see how many valence electrons an element has. One way of finding out is something that we've already done. We can do the electron configuration. All right, so just kind of show you, let's kind of pick out two elements. Let's do sodium and chlorine. Okay, now how many electrons does a sodium atom have? 11. Okay, has 11 electrons. Now how many protons does sodium have? 11. Because remember, atoms are electrically neutral, so that means that the number of protons, number of electrons are equal to one another. All right, so if we do the electron configuration, anybody remember how to walk me through that? What do we start out at? 1s. How many electrons in 1s are we going to put in? 2. Then we're going to go to 2s. How many electrons there? 2. Then we're going to go to 2p. How many electrons there? 6. Then we're going to go to 3s. How many electrons there? 1. Okay, because sodium's in that third row, starts the third row. So 3s 1. Now, looking at the electron configuration, what is the highest or the outermost energy level you see? 3. Okay, how many electrons do we have in the 3s? 1 electron. Now let's look at chlorine. How many electrons does chlorine have? 17. How many protons?
17.
Okay, so let's do chlorine's electron configuration. We start off with
1s2.
1s2, then we're going to go to
2s2.
2s2, then to
2p6.
2p6, then to
3s2.
3s2, then to
3p.
3p, 5. What's the highest energy level for this one?
3.
3. How many electrons do we have in the third energy level?
7.
7. Because we have a 3s sublevel and a 3p. So we add up those number of electrons, 2 plus 5, grand total, 7. Okay? So this is one way that we can figure out how many valence electrons an element has. Or we can kind of use a very simple, easy way. Choice is yours. This way or the simple, easy way?
Easy way.
Okay. This works for the main group elements. Group 1, 2, 3, 4, 5, 6, 7, 8. So we're going to be leaving out the transition metals and the intertransition metals. Okay? Alright, so elements in group 1. Where's group 1 out on the periodic table?
The very left.
Yeah, the very left. First column on the left-hand side. Group 1, they are going to have 1 valence electron. Well, we kind of saw that with sodium. So if we did all the electron configuration for all the elements in group 1, their highest energy level would only have, bless you, 1 valence electron. Okay? Now if we go to group 2, guess how many valence electrons they're going to have? 2. 3 is going to have 3. 4 is going to have 4. You kind of seeing the pattern here, ladies and gentlemen? All right, so 5 is going to have 5. 6 is going to have 6. 7 is going to have 7. And 8 is going to have 8. Right? Okay, so if we know where the element falls at, if it's in one of these groups, we know how many valence electrons it's going to have. Any questions there? No? Okay. Now, one more way that we can show valence electrons is we can do what is called the electron dot diagram. So hopefully you can kind of figure out what we're going to use to represent the valence electrons. We are going to use dots. But for this one, sometimes we might not have to, we might not use dots, okay? But whatever symbol you use for the valence electrons, you got to keep on using that same symbol over and over and over, okay? So let's kind of look at an example of how to do the electron dot diagram. Well, we're going to pick an element from each of the main group elements. So from group 1, let's do lithium. Okay, so electron dot diagram, we write down the symbol for the element. Then we're going to imagine that there is a square around the symbol. Now, a square has how many sides to it? 4. Now, lithium's in group 1, so it has 1 valence electron. So we're going to put 1 dot to represent that 1 valence electron. Okay? Any questions there? All right, let's go to group 2. Lainey, pick an element from group 2, please.
Calcium.
All right, calcium. So, since calcium is group 2, we're going to have 2 valence electrons. We're going to have 2 dots. Now, with my OCD, I always like to start at the top. But you don't always have to start at the top. You can start on whatever side you want to. Okay? So 2 dots. I'm going to put 1 dot up there. And I'm going to put the other dot on the side of calcium. Now, why didn't I put them both together? Well, when we're doing the electron dot diagram, we have to have at least 1 dot on each side of the symbol before we can have 2 dots on one side. And if we go to group 3, do boron, so it's going to have, since it's in group 3, it's going to have 3 dots. 1, 2, 3.
So if I
do I have to put my dots how I put them last time? Or like,
for me, I always start at the top.
I know, but like,
But you could, I mean, if you want to start on this side and work your way around, that's fine. You just need to have one dot
that's
on
not
each
what
side.
I'm saying.
The dots have to be in a specific part of the line,
I just
like on each side. Is there a specific spot where it
No,
has to
just-
be?
I just start on the left because, like I said, with my OCD, I just start on the left-hand side. I just want to have one dot on each side of the element.
Okay, that's not what I'm saying. But like, how there's two on that one, then you go over. Do my two dots have to be in the same place as they were on the other one? So I can like move it around each time?
Yeah, that's what I was trying to say. You don't always, for me, I always start at the top and work my way around. I work clockwise. You can start at the bottom and work, counterclockwise or clockwise. But for elements in group 3, we need to have 3 dots and needed to be in sequential
No.
sides. So one right after the other, okay? We can't have, for calcium, we can't have one over here, one over here.
That's what I was at.
Okay, no, we have to go kind of in
Okay.
clockwise or counterclockwise
Okay.
pattern. All right, so now, if we go on to group 4, we have carbon. So we have 4 dots. 1, 2, 3, 4. Okay? Now, with groups 5, 6, 7, and 8, we can start pairing up the electrons. Okay? So group 5, let's use phosphorus. 1, 2, 3, 4, 5. Okay? Questions? Any kind of questions? All right, group 6. Cole, pick an element from group 6, please.
CS. Is that it?
No. Group 6, the column.
B.
Keaton, pick one from group 6.
Sulfur.
Okay, sulfur. Group 7. Ethan.
ROE.
What?
ROE.
Columns, ladies and gentlemen. Group 7, let's go with fluorine. Group 8, let's go with.
I see that.
It's still going. We're going back to each groups.
Okay. So work on those 3 real quickly. Look at the Roman numerals, ladies and gentlemen. 1, 2, 3, 4, 5, 6, 7, 8.
That's why we were all confused.
Oh, I didn't know that.
So we just skip the part that's like,
That's what I said.
You skipped that in.
yeah.
We're jumping over the transition metals and the intertransition metals.
Yeah, I should probably keep this here. So we can do that one. I thought we were just talking. Yeah, so I said totally different ones. So the thing is, jacked. This little stand. Because you put it here and it just goes. Can I hear us? He's so hard like working doing those for 30 minutes. And then you get to do whatever you want. Dude, my freaking oh, I'm so sore. I was gonna say something and I forgot about this camera.
Yeah, man, I didn't even sleep for only like 5 hours.
All right. Sulfur. 1, 2, 3, 4, 5, 6.
Would you be able to send Cole Davis down to the tech office with this Chromebook?
Yes.
Thank you.
Do we have something like this?
Mm-hmm.
Two sequential sides that had 2 electrons to them, and then the other 2 only had 1. Okay, now for fluorine, what I'm going to do, instead of using dots, I'm just going to use X's to represent the valence electrons. Okay, so fluorine, we have 1, 2, 3, 4, 5, 6, 7. So 3 sides with 2 electrons to them, 1 side with 1.
Yes.
Okay, neon. 1, 2, 3, 4, 5, 6, 7, 8. Each side has 2 electrons to it. Any questions?
How come you switched up your symbol? Just all of it?
Just to do so. Also, since they're right below these, I didn't want people getting messed up with which one is which. But like I said, with the electron dot diagram, if you want to use dots to represent the valence electrons, do so. If you want to use another symbol, you can do that. But whatever symbol you use, stick with that symbol. Okay? All right, so now, why do elements become ions? Well, what they're trying to do is they're trying to become stable. They're trying to reach a certain amount of valence electrons. How many valence electrons do you think they're trying to get to?
8.
8. Why?
Because at that point it's stable and they can't get any more
Right, they're stable. So, group 8. What's group 8?
noble gas.
Noble gases. And they're inert, if you kind of remember, they're inert gases because they don't really react with any of the other elements, right? Okay, so the other elements will gain or lose electrons to reach 8 valence electrons. And what we do is we call this the octet rule. And what the octet rule is just for basically reach 8 valence electrons. So let's go back to our 2 elements right over here. We said that sodium had 1 valence electron, right? And it's trying to reach 8 valence electrons. So for sodium, would it be easier to lose that 1 valence electron or to gain 7 more valence electrons?
Mhm.
All right, so if we lose 1, we lose that 1 and 3s. Our next highest energy level is the second energy level. Everybody see that? How many electrons do we have in the second energy level?
8.
8. Okay? So now, sodium will always have 11 protons, but now it has 10 electrons. So we have an offset of protons and electrons. We have 1 more proton than an electron. Agree? So as an ion, sodium would have a +1 charge. Okay? Now chlorine, we said that it had 7 valence electrons. Would it be easier to gain 1 more electron or to lose all 7? Gain 1 more. So what's going to happen if we had sodium and chlorine next to one another? That 1 valence electron in the 3s that sodium had is going to go to chlorine. Now, if we look in the third energy level, we have 8 electrons, right? How many electrons do we now have total? 18. We have that offset of protons and electrons. We have one more electron than proton, so chlorine would have a
Negative ion.
negative charge. It would be a negative ion, an anion. Okay, any questions there? So, can we kind of see it this way? No. Let's kind of show it with the electron dot diagram. Alright, so sodium has 1 valence electron, so we use 1 dot to represent it. Chlorine has how many valence electrons? 7. 1, 2, 3, 4, 5, 6, 7. And we said that that 1 valence electron from sodium is going to go to chlorine. So sodium has a +1 charge, chlorine has a negative charge. And what's going to happen is that we're going to have an attraction now because they are oppositely charged to one another. So sodium with a +1 charge combining with chlorine with a -1 charge, and we're going to get NaCl. What's NaCl? Table salt. Okay? So this is all section 1 right now. Does anybody have any questions right at this point? Nope. Okay, let's go on to section 2.
Where do you get the plus and minus? It's just coming off of 1, or try to get like 8 on the end of the CL and
All right, so what I just showed you was we created an ionic compound. Ionic compound. Compound composed of cations and anions. And what we're going to see when we do make compounds, we're going to have some kind of bond in it. So we made an ionic compound. Guess what kind of bond we're going to have? Ionic bond. Okay, so an ionic bond it's an electrostatic force of attraction between cations and anions. So with an ionic compound, we're always going to have positively charged ions combined with negatively charged. Are we ever going to have an ionic compound with 2 positively charged ions put together? Answer is no. Because if we try to put a positively charged ion next to another positively charged ion, what do you think is going to happen? They're going to repel. It's kind of like magnets. If we put north pole to north pole, they repel one another. But if we put north pole to south pole, opposite poles, they attract. Okay? Now, a couple of things about ionic compounds. Ionic compounds are crystals at room temperature. So yes, table salt, that is actually a crystal. They have a high melting point. And they can conduct electricity when they are melted or when they are dissolved, usually in water. That's why they say don't go swimming during a thunderstorm, because in the pool there are compounds, more particularly ions. The ions are the ones that conduct electricity, not the water. So if you went swimming in a pool full of distilled water and we were able to get all the salt off your skin, and the only way that I can kind of think of getting the salt off your skin is taking like sandpaper and being very abrasive against your skin. And if you wanted to try that, I mean, not going to tell you to not do it, but I advise not to. You can try doing that and you should not be able to get shocked. Or you can stand in a bucket of distilled water and get all the salt off your skin from your feet up to about your knees and everything, and put a live wire into there. And there are some people that would love to try that. Okay? Questions? Any kind of questions about ionic compounds?
Nope.
No? That's section 2. Section 3.
It's a review. I know. I hate you.
Okay, section 3. Is on metallic bonding. Now, metallic bonding, what do you think we're going to be looking at? Metals, okay? So what is actually a metallic bond? Okay, this is what the book says metallic bonds are. Forces of attraction between free-floating valence electrons and positively charged metal ions. If we were able to kind of look at cross-section of what a metal would look like. Here's our metal cations, okay? Then around them are all these valence electrons. And since these metal cations are around all these free-floating valence electrons, they say that they are in a sea of electrons. Anyone ever been swimming in the sea before, the ocean? Okay, so swimming in the ocean, kind of floating around, all of a sudden a wave comes in. What happens to you when that wave comes in? If it's not really high tide, you just kind of bob up and down, right? Nothing much happens. This sea of electrons kind of acts as the same as a buffer or a barrier against forces that we see in, and it gives the metals properties that we don't see in anything else. Because if we put pressure onto a metal, does it usually break real quickly? No, okay. So this sea of electrons, the two properties that we see with metals that we don't see with anything else are these. So the first one is malleable. What malleable means, it's the ability to be hammered into thin sheets. Alright, so if we're working with a really soft metal, we just put it on the tabletop, take a hammer and start hitting it, and it'll flatten out. Now some metals, you gotta heat them up so that they can actually do that. You gotta watch Forge and Fire, they talk about that a lot. They heat up the metal in the forge, take it over to the press. Since it's hot enough, it will work the metal so that it's malleable. You take an ionic compound. For example, chalk. Chalk is an ionic compound. If I had a piece of chalk right here and I took a hammer to it, what would happen to it? It would just shatter, okay? The other property that we see with metals that we don't see with other types of compounds or anything, they are ductile. Now what ductile means is just the ability to be drawn into a wire. So how companies make copper wire is they take a piece of copper wire and they put it into a press and they push it into, you know, whatever kind of hole, whatever kind of gauge wire they want to, and it comes out that way. Because the sea of electrons allows that force to be evenly distributed and it doesn't break it apart. Questions? Any kind of questions? Now, when we're working with metals, a lot of times we're not going to be working with one particular type of metal. We have a mixture of metals. What do we call that mixture of metals?
Alloy.
Alloy. Okay. So alloy, mixture of two or more metals. Now, why do we mix the two metals? This is the biggest thing. Alloys are stronger than individual metals. Okay? What kind of questions do we have? No questions? Well, ladies and gentlemen, that is chapter 7. We are done for today.
I think there's 4 things.